So now in this video, we're going to do some quick step-by-step builds of basic op-amp circuits here, used as a comparator. We're going to use a couple of different voltages. First 5 volts, and then we're going to kind of simulate lithium iron phosphate batteries by being in about the 12.8 volt range, down to 12 volts and up to 14.6 if a charger is attached. But a fully charged lithium iron phosphate battery not being charged is for 13.6 volts. But in any case, if it's a 12 volt lithium iron phosphate battery. Here we have an op-amp. We're going to use 1 out of 2, so you can see there's 1 on that side, 1 on that side. First off, though, you have to put the positive supply to pin number 8, negative supply to pin number 4. Maybe it's a more negative voltage than ground, but in any case, a lot of times ground is the most negative voltage there. So we already have that on the board right there. Now I'm going to have to put the load up here because we're going to kind of clutter this with components going to the inputs. So one thing to pay attention to when you're looking at the schematic, first off, they may not show the power pins on the schematic symbol. Generally it's the same voltage as everything else that you power the op-amp with. There's 2 op-amps in this integrated circuit. And so we first are going to set our reference voltage for a non-inverting comparator using an op-amp at 5 volts. And pretty much regardless of the voltage, you can go relatively high because these are 10,000 ohm resistors. 10,000 ohms is commonly used for voltage dividers, so it's good to have a bunch of those. If we put 2 of them in series, we will get half of the supply voltage to that input, and so we'll look at what that means later on. So I'm going to put this, that's to the output, the very top. I have the power turned off, by the way. We have 5 volts right there. Current is off, and power is turned off for the output there, and it's automatically turns on when you plug it in. And then we'll put that one to the negative supply right there. Now what I'm going to do, that gives us our reference voltage. I'm going to put a jumper for the trim pot, because the trim pot's kind of an awkward component. So we have the inverting, the negative on top, and the non-inverting positive on the bottom there on the schematic. That's not always the case on the schematic, but whenever you're using an op-amp component, the positions that they are on that component are fixed. So don't go higher or lower based on the symbols there. Make sure they match with the op-amp, and invert them on the actual circuit as needed. Something to always be aware of when you're looking at op-amp or comparator. Comparator is a component that behaves like an op-amp being used as a comparator, but it does not, cannot be used as an op-amp. So there, we got that jumper to bridge the gap with this trim pot. So I need to get a couple more jumpers for the supply pins going to this trim pot, and it looks like that may be one of those pins might be a bad spot. So that's another problem with these breadboards. I got like a few spots that got damaged, and so components can't really be inserted in them. I have to work around them. And actually I did have the supply pin. So I already planned this out when I inserted the resistors up there. The supply, negative supply right there, is in kind of an awkward position. And so I'm just going to diagonal this one. So it's a little bit longer than this jumper wants to do right there, but it works. So now I kind of pre-added these jumpers to save time. That goes to the positive supply. So now that row is a positive supply. This goes to negative supply. Now that entire row is negative supply once I apply power, of course. So this little kit here, you commonly see them like this. I have the jumpers for 2 of these kits in there. I kind of crammed them in there because I busted one. The lid broke off, and I'm using up pretty much all my gray jumpers here. I may have lost a couple. So probably you want at least 2 of those kits. But in any case, we're going to light a couple LEDs. So you see them touching the output. Doesn't matter the order right there. The blue one, we are going to connect to the positive supply. So that is the long lead, the anode, where we don't have the bar. So if you don't cut it, the long lead, and the cathode is a little shaved on the side. If you won't pick it up on the camera. But if you haven't trimmed it, it's the shorter lead right there. And we will set that off to the side there, I think. And then we got the red one right here. So now, when it comes to the red one, so the short lead, the cathode, that heads to ground. And so we got the shorter lead right there. We got the longer lead, the anode. I'm going to go up one spot. So short lead to the negative right there. Got to put it in the right way or else it won't light up. 5 volts won't damage it. If you accidentally put it in backwards, it just won't light up. Let's do the 1K resistor first. So blue LEDs are naturally brighter than red LEDs. So most of the time I use a higher value resistor to protect the blue LED from the same voltage as the red LED. Sometimes I just want to keep it simple. If the red LED needs a 1K resistor, then often I'll just keep using a 1K with the blue resistor. Keep it simple. So yeah, that's down to its cathode, the shorter lead. So that LED, you can see we got positive there. The blue LED will turn on when the output's low. It connects to ground pretty well when the output is low. That's what it's going to mean when I say the output is low. And hopefully the blue LED helps, there you can see the path right there, helps to make it more understandable what I mean by it's low. And then the red one. So now I got to stretch this up to the anode, which is a nice thing about resistors right there. So resistors are a lot more, they can stretch across the board far better than LEDs. So, you know, put the LED in first most of the time, you know, position it. So that is it for our wiring. Again, only 220 ohm resistor for the red LED. The output doesn't get to 5 volts. This is a component like the 555 timer that connects to ground really well, but does not connect to the negative supply terribly well. And oh, that's the cable right there. That's casting the shell. So let's test this out. So first off, it is, I'm sorry, I got some components clustered there. I didn't think they would show up that far away. We turn the power on. So it's comparator. We set our reference voltage at the inverting input, the minus. So right now the trim pot is all the way to the positive supply. We're getting 5 volts, and there you can see the output is high because it's above 2.5 volts. Somewhere about halfway you'll see the blue LED light up right there. And some circuits may have a problem right at the halfway point, but it looks like this one I kind of like really struggling to try to get a halfway point where they might be both on or something. And maybe they made it so it won't be both on. But there we go. I dropped it lower right there. A lower voltage for our signal right there than our reference voltage gives us a low output right there. So that's the non-inverting comparator, and we wired that at 5 volts. So now we're going to jump over to my inverting comparator schematic. So it might look exactly the same. The main difference here on the schematic is that you can see we got the negative now on the bottom, the inverting, and the positive on top, the non-inverting right there. And there we can see the pins, of course, the negative is on top, the positive on bottom on the physical component. So always pay close attention to that. It may be swapped on the schematic, but you can never swap it on the physical components. It's always the same. So we got the top input there, the minus. We are going to put the trim pot. That's our reference voltage, just because we're not blocking the view in this area at all right now. That's why I'm going to wire that one first. So that is our signal voltage right there. We can adjust that. It's to the minus right there, even though it's higher on the board and lower on the schematic. That's something easy. That's easy to mess up. And let's see if I lost that. Okay, didn't take that long to pluck the resistor out of kind of a cluttered spot. So yeah, I'm gonna put this up here out of the way, and then put a little bit closer to the input right there. There's one of our 10K resistors to the positive rail, and then over to our input, and we're gonna make our voltage divider again. So again, I explained what a voltage divider is. Actually, if you're learning op amps, you should already understand fixed value voltage dividers. If a voltage divider is confusing for you, watch a bunch of videos on voltage dividers. Very important to understand. So yeah, now we are done wiring it up, but actually we got these two inputs right there. Right now I'm going to grab some jumpers. So technically you should not leave inputs floating, and I don't think its power supply is off. If I accidentally short the output, that top one, it'll be a short circuit. My power supply will turn off to protect the circuitry. But still, best to avoid that. So yeah, we're going to put that jumper in again. Yeah, I think I got a bunch of these yellows, and I wanted to do a gray, but looks like we'll have to do yellow. And I did have an orange. I could have just plugged. But yeah, I could also just slide this over to the negative supply. I don't think positive or negative matters. But in any case, if you tie the unused inputs, so that's an op amp we're not using, it helps stabilize things. Otherwise, it might the output might oscillate and other stuff might oscillate, and it might affect the integrated circuit and maybe even the circuit you're working on. So it's best to always apply the power, but I don't always do that, just to keep the video simple. So now I'm going to turn power on again, and again we're using 5 volts, so that's the value components that I based it on. And so I'm going to turn that on there, and so now the trim pot is actually a lower voltage. We don't really need to see that there. So there, it's a lower voltage. It's pointing to ground, as you can see right there. And you know, it can be anything lower than half of the supply voltage, halfway. This is a variable voltage divider using a trim pot when you use all 3 pins. If you only use 2, the wiper is the one in the middle. If you only use those 2 or those 2, then it's a variable resistor. This is a 10,000 ohm trim pot. It's probably like closer to 11,000. It's usually slightly higher than its rated value. But exact value doesn't matter. It's the percentage of the way up towards the positive supply or the negative supply when it comes to the output voltage. Again, this isn't to provide power, but in any case, you can see we got a higher input than our reference voltage. We got a low output. We got a lower input voltage for our signal than our reference voltage, so lower than reference. We got a high output. It's inverted right there. So whenever you want the output to be in the opposite direction of the input, you can just quickly wire up a inverting op amp comparator circuit, or you could use a comparator, but their outputs are different. So now we're going to come to another diagram that I covered this in more detail before. This is a review, same with the other diagrams. So this is kind of the range of voltages you can expect if you're using lithium iron phosphate battery, a 12 volt lithium iron phosphate battery, which actually has a nominal voltage of 12.8 volts. Most of the time you use it, it's going to be about 12.8. But if you have a charger attached, they go up to about 14.6 volts right there. You don't want to go above that. Some of them could be like a little bit lower, but you might be dealing with 14.6 volts. With the charger attached, you remove the charger, the battery quickly just drops down to 13.6. So that's its fully charged voltage. But if you apply a charger with a higher voltage, it'll pump more current. You'll get more power out of it in the long run if you charged it to a higher voltage initially. So in any case, always consult the data sheet, any component you're using. But if you look up LM358, review the data sheet, you should see that it can handle a single supply of 3 volts to 32 volts. So yeah, you could work with pretty low voltages, or relatively high voltage right there for an integrated circuit. Some integrated circuits can only handle about 5 volts. You really can't vary or drift away terribly far from that. You might damage it, or it might not work, whether you go up or down. So in any case, this integrated circuit easily handle 14.6. Now you see dual supply here. What that means is, the most negative voltage is not always ground. Sometimes ground is halfway between a positive voltage and the same voltage that's more negative than ground. And so we can kind of like change the direction the current is going right there. But when ground is the halfway point, then it's really easy to change current direction from any part of the circuit. Hopefully that makes sense. Otherwise, just do a YouTube search of dual supplies and watch a bunch of videos. It'll come to you sooner or later. So we are dealing with a higher voltage if we use a 12 volt lithium iron phosphate battery. So first off, we can't exceed the current of the blue and red LED. If we use the same resistors we're using in lower voltage circuits, the current through the LEDs are going to go up. So first off, we need higher value resistors to make sure we don't put too much current through the LEDs. And then we have these higher value resistors. We got higher voltage. So since there's higher voltage, even if you had the same current as a lower voltage circuit, because you changed the value of the resistors, there's more voltage across your new resistors. So even at the same current, they're going to get hotter because they got to dissipate more power due to the higher voltage. So I did the math a long time ago, but these should be perfectly safe to get probably about the same amount of current we got with at 5 volts with the lower value resistors in earlier videos. You know, these will probably get like a little bit warmer, and that's just something you got to calculate. Make sure they don't overheat. So otherwise, this is the inverting comparator. So our signal goes to the plus right there, which is actually the lower pin on the integrated circuit, as we saw earlier. Our signal is to the minus, so it's inverting. When this gets a higher voltage than what we set there, which is half the supply voltage, output will be low. When this gets lower than our signal, or than our reference voltage, signal lower than reference equals high out. Remember that. And again, we're going to lose about 1.5 volts probably coming out. Even as the voltage goes up, you lose about the same from the positive supply, just because that's how this integrated circuit is. And so it's not rail to rail output. It's mostly meant to connect to ground extremely well and to the positive supply fairly well, but not perfectly. You lose a little bit of voltage. So we had this wired in the last video. So now, a quick edit. I kind of goofed. I had a 15K resistor instead of 1.5K. This is 1.5K right now. They put the K where the decimal point should be, because you might not see a decimal point. As you can see, it's pretty sloppy there, but you can definitely see the K. So, in any case, I know this has a 5 in it because it's got a green band. The one that I got on the board, I also have my, that's the 3000 right there, that's orange. And I got the 5K, the green band there. So yeah, I plucked them out of the bags, but I, wasn't thinking or whatever. I had a 15K, and the red LED was really dim. I was trying to figure out why. I don't even think I was getting 1 milliamp of current through it. So yeah, we got 15K power supplies off right now for that one. And again, as I said before, this is a green band. I know it's 3K because I grabbed it out of the bag that says 3K. And so I also made a mistake in the last filming. I put the resistor to the positive supply there, so the blue LED did not light up when it should have. So I move it down there. Now it's in the right spot, down to the cathode. So I just thought I would mention that. It's mistakes happen. I filmed that. I planned to show that I filmed that, but when that was 15K, it was just kind of a waste of me fumbling around and wondering what's going on and stuff. And so I figured I would just tell you about that. So I have the power supply set to 15 volts. Again, that's just a little bit more than 14.6. So if you can make it safe for 15 volts, it's safe for 14.6. There we go. Now you can see the red LED. Not lit too bad. And we have 9 milliamps of current. So now if I pluck the red LED, we're still going to have about 2 milliamps of current right there. So that's going through the voltage dividers that we are using. So there's still a bit of current going through them to be aware of, because we're dealing with such high voltage. And now it's getting to be relatively low value resistors for our voltage divider. So a low input there, red LED. And then a high input blue LED, because we have a higher voltage than our reference voltage, but it's inverting. So higher voltage, low output. Lower reference, or lower signal voltage compared to reference voltage. High output there. Red LED. Positive going that way. Stuff we covered before. So we're going to move on. And finally, we're coming back to the non-inverting comparator. So really, it's all the topics we covered before. We got the higher voltage. That's what we covered before. It's the main difference between this one and the first circuit we looked at, which was a 5 volt, non-inverting comparator. And also, I didn't show the voltage range with the inverting comparator, so I'll do that again. So yeah, I should always turn the power off when you rewire right there. Sometimes I don't. Well, I kind of quickly going through things. If you're really careful, there should be no problem, but if you miswire something, you could short circuit. So all I'm doing is lowering all these jumpers that go to the trim pot one spot right there, so that we move back to putting the jumper at the the trim pot, I should say, to the non-inverting comparator. And I think that's the better way. Either the arrow, whatever direction it's pointing, that's be higher or lower, whether you do it that way. But I don't really like pointing towards the op amp as much. So generally I do it this way, where the arrow will point away from the op amp. But it doesn't matter, whatever you prefer. And yeah, we got a bad spot in one of those 3 pins. So yeah, I just kind of gently kept rotating and trying, and finally just popped right in for whatever reason. So I usually don't have that much problems with the trim pot. So yeah, I'm going to go wider there on both sides. Then what I'm going to set, so that's to the positive. Then what I'm going to set with this one, keep them a little bit closer right there. And so they shouldn't touch, but you could also, you know, kind of push this out of the way, push that out of the way. If you're not trying to film where, you know, you're not worried about what other people can see. If I look at different angles, you know, I can clearly see what's going on. So yeah, that's it. Again, we will get the power supply back. That's all we did was swap the two positions because we went from inverting to non-inverting. So if you just notice, hey, this is doing the opposite of what I want, you just swap which input your reference voltage and your signal go to. So yeah, we got 15 volts. As I said before, this will work plenty fine down to 12 volts as well. Of course, there's going to be a little less current. Components are going to get less hot and whatnot. But we, you know, want this to work safe at the maximum voltage we can expect. And again, so now we are less than like half the supply voltage. We know that because we have a low output. The signal, I mean less than the reference voltage. Signal is lower. It's towards ground, blue LED, low output. Signal is higher than halfway. And now we have a high output right there following. So again, all stuff we covered before. And hopefully most of the stuff I mentioned in this video was stuff you already know. In fact, this is kind of like just meant to be a review video. If any particular topic was kind of confusing, again, just look for YouTube videos, or if you like reading, looking at schematics and stuff, do a Google search of whatever that topic is, whatever word I had mentioned, and you know, read or watch as much as you can. At some point, one person is gonna say something that just magically you understand. I have books where I remember I was reading this particular spot when I finally understood this particular topic. And so that happens. So just keep listening to different people if one person explains it in a way that you don't understand. It's nothing personal, it's just different people relate to different things. And so whatever that particular person heard, where they finally understood it, they repeat exactly what that, or you know, basically what that was. And then somebody else will be like, okay, yeah, now it makes sense. That's just the way it goes. So in any case, rambled on long enough. Thanks for watching. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.